much for inviting me. So, as the title the slide tell you, today I'm going to tell you about our recent work on predicting noise-induced critical transitions in a class of multiscale dynamical systems. In particular, the method that we are going to use will involve reservoir computing that I'm going to tell you more next. So let me just give you a brief outline of what I'm going to talk about. So first, I'm going to start with some introductions, and then I'm going to tell you the prediction problem that we consider. So basically how we formulate the problem and what is the setting. And then I will tell you about our proposed machine learning based solutions. And then I will show you some numerical experiments and the results. And in the end, I will make some conclusions. Okay, so to begin with, let's consider these non-autonomous, non-linear dynamical systems of this form. So basically, X is the state of the system, which is usually is metastable. And this F is the vector field, which is typically non-linear. And then there's a driving signal, which is supposed to be noisy and fast. So this small f of t. And let's think for the special case when this capital F, the vector field, this is modeling, let's say, a double well potential. And in this case, then the signal, which is fast driving, will induce transitions from one stable state of the system to another, right? So this is what I refer to as signal-induced critical transitions, or some people call this tipping point. So there's this famous paper by Aspin et al. That study tipping points in the context of climate science. So anyway, so another interesting thing to note is that so usually this fast driving signal is external to the system, but usually f of t may come from another dynamical system. So then basically you have two systems. The first one is a system with state X. Another one is a system that destroys f of t. And these two systems interact with each other. And you can view X as open dynamical system, in the sense that without the small f of t, it's a closed system. But with f of t here, it's open because it now interacts with another system. So that's another point of view. But in this talk, we are going to assume that there is a separation of time scales on which the system state and the signal evolve, and consider the following slow, fast, non-linear dynamical systems. So here, as you can see, the signal is taken to be the following structure. So there's the scaling in terms of the small parameter epsilon here. And there's the vector field, capital G and capital H, which is typically, again, non-linear. And so what this small parameter epsilon means, right? So, yeah. So the idea is that if we take epsilon to be smaller and smaller, right, then under some assumptions on the vector field G and H, stochastic behavior emerge in this system. So, so under what type of assumptions? So I think there are various papers on this that try to study. This is so-called the problem of the so-called deterministic homogenizations, where as the limit of the small parameter epsilon goes to 0, you get a stochastic differential equations. So basically, the assumptions that one typically imposes is that so the fast flow has compact attractor with the measure supported on this compact set. And the vector fields need to be sufficiently nice in the sense that, let's say that some leak stick conditions and boundedness conditions hold. And the G, so remember G is this guy here, averages to 0 under the measure. And I think more importantly is this so-called mild chaoticity assumptions, in the sense that the fast flow has to be sufficiently chaotic. For example, the so-called weak invariant principle, or people usually refer to as a functional central limit theorem, hold for the fast flow. So then under these assumptions, one can prove that the slow fast systems earlier converges in law to the following stochastic differential equations. And so this is, you can get all this result basically in this paper of Melbourne and Stewart in 2011. And so now a few remarks about this. So it turns out that, okay, so just to recap, so the theorem basically tells us that we can view the slow fast systems earlier as approximations of a SDE model. And then in fact, there are many ways in which we can extend this theorem. So these are some of the references that you can refer to. And in particular, recently people have been able to find rich connections between the homogenization of these systems to rough path theory. So we are not going to talk about the rough path setting here. So we will be mostly talking about within the setting of this theorem. So everything is just sufficiently nice, and this system here will converge in law to SDE as S1 goes 0. So that's it. So this is the setting that we are in. So example is that, well, easy example that we can think of is this bistable system driven by a fast Laurent 63 system. So so basically the Laurent system here is the one with the classical parameter values that lead to a chaotic behavior. And then in this case, the assumptions that I showed you earlier holds, and indeed you can prove that this system basically converge to this SDE in the limit as epsilon goes 0. Okay, and so there are various applications of this system that you can find in this paper. So now I'm going to introduce the prediction problem. So let's say that we consider this system. So this is basically, again, a slow fast system, and we are only interested in the variable x, and not so much about the fast variable y2 here. So so we can, let's say that we have access to data for x, and it looks like this, right? So it's a bistable system. So at the initially it will fluctuates around potential minima, and then after some time, at some seemingly random time, it will jump, right? It will, I mean, the state will transit to another minimum here, and so if in the case that the noise amplitude is small, then this transition is a rare event. And our goal here is that we want to be able to predict this jump, the transition here, using data for x. And also the data for x does not actually record any occurrence of this transition beforehand. So basically this is assumptions that I just told you. So again, so we are going to assume that we only have access to data for x, and the data is sufficiently long and high frequency. and the data does not record any occurrence of a transition event. So for example, the data is before this yellow dashed line here. And then we don't have any data for the fast variables, fast process. But we assume that we do know something about, like, let's say that we know some physics or system. So we assume that we know the force field F is known to us. So then there are a few questions that one can ask and try to solve if possible. So first thing is, can we predict if and when a transition event will occur in a given future time window? And then if so, can we infer the characteristic of this event? How far in advance can we predict them? And then with what accuracy and certainty can we achieve these goals? And maybe more ambitiously, is it possible to do all this with a computationally inexpensive methods and or using a relatively short time series for X? So we just try to think about this, and then eventually we come up with a 3-step procedure to tackle this problem. So the first step in the procedure is that because we realize that the problem is actually multi-scale, right? So even though if we are given data for X, we need to be first able to extract the fast driving signal using this data for X. And also and also the norm expressions of F for F. So we can extract the fast driving signal from the data. And then after that, we are going to use machine learning. So basically, we are going to use this extracted signal as a training data. And we are going to predict into the future the values of this signal. And then after that, we can plug in the predicted values of F into the system, and then we can numerically evolve it into the future time. And then the predicted value is basically obtained from the resulting numerical solutions. So this is the 3-step procedure that we use. And now there's a choice to make here. So in step 2, there's this supervised learning step here. So we need to decide what type of machine learning method that we should use to do this. And because in this example, the fast flow is basically just the Lorentz system, which is chaotic. And reservoir computing seems to be best suited for predicting chaotic systems, as demonstrated by many papers in recent years. So we are going to implement step 2 using the so-called eco-state networks from reservoir computing. So I'm going to tell you more about this eco-state network next. So if you don't know about eco-state network, basically, so this network comes from the paradigm of reservoir computing. So this paradigm actually treats the network as a randomly generated dynamical systems. And then not all parameters in the networks are trained, only the parameters in the last layer of the network is trained. And because of this, then basically we reduce the learning problem to simply solving a linear regression problem. And this has several advantages. First, in comparison with gradient-based optimization methods, we don't have to worry about the issue of vanishing or exploding gradient problem. And then the training can be done in very fast. So everything is cheap here. And moreover, it has some theoretical guarantee in the sense that these eco-state networks can be shown to be a universal approximator of arbitrary dynamical systems. And then it actually is backed out by many works recently that shows that this network is able to achieve excellent performance in many benchmark tasks, such as the one like for predicting chaotic systems. And these are just a few papers that support this this point here. So anyway, so now I'm going to tell you about what type of architecture of ecosystem network that we use. So we use both shallow and deep ecosystem network. So by shallow ecosystem network, we means the network rules out the equation looks like this. So here the X represent the hidden state of the network, and Y is the output. So basically we feed input. So input is denoted by U, which is the training time series. So we put, so at each time, we basically feed the input into the hidden state and then evolve it in time. And then at each time, we get the output by basically transforming linearly the hidden state. So this is what we call the shallow ecosystem networks. And then we also consider a deep version of ecosystem networks in the sense that now the outer equations is not, it becomes hierarchical, right? So, so here the input U is here. And then before this, there's a hierarchical stack of this hidden state here. And then the output is computed against by linear combinations of the hidden state and bias vector. So again, in the spirit of resolver computing, we are keeping this W, W0, WL, and the MB. So all this as fixed matrix. So these are basically random matrix. And then we only train the parameters in W out. And also here we are adding noise, the C, N, or L for regularizations. So this is our deep version of the ecosystem networks. And why we consider this version? Because intuitively, increasing the depth of this network can actually lead to a better multiple time scale representation of the temporal information. So, so later I will show you by experiments that using the ecosystem network can actually, in some cases, help with these multiple time scale representations. So this is a picture to summarize what I have said so far. So again, you have training time series, and then over time, you are going to feed this input into the network, and then you only train. So all the parameters in this network are random, and then you only train the parameters in this read out layer, so W out. So so there are more details about this. So maybe I shouldn't go more into this, but the idea is that it's actually not too straightforward to train this ecosystem network because once you initialize a network, so basically it's a randomized network, you need to make sure that it has certain property, the so-called equal state property that will allow that will basically make sure that everything will be okay when you train it. So the intuition behind this equal state property is that you need this property so that the reservoir, which is a random dynamical system, will asymptotically wash out any information for the initial conditions. So then the dependent on the initial conditions will be eventually forget. So these are some details on how we select these random matrices here. The details are not very important. So I'm going to basically skip all this. But one important thing is that we need to rescale these matrices so that they have spectral radius that is less than 1 to ensure stability of the system. So then, as I told you earlier, after you initialize the network appropriately, so that it satisfies the equal state property, then we can train the readout by simply solving a least square linear regression problem. So these are the details, but again, it's just basically solving a linear regression problem. And with this, we complete the training phase. And then in the prediction phase, so in the prediction phase, we no longer have the data, right? Because we are trying to predict the system into the future. So what we do is that after we obtain the trained network, we are going to propagate the network autonomously for predictions. So basically, we replace the U. So U originally in the training phase is our training data. Now we don't have training data anymore. So we are going to replace U in the update equations by this Y, which is the output from the previous time step, basically. And then after that, we get predicted values, and then we complete the prediction phase. So, so because we are really in the machine learning setup, so it's important to do careful model selection and validation. So I'm not going to go into the detail of all this, so I'm just going to give you some brief ideas of how we do this. So let's say that we are given a data set. So we are going to assign first a training set, validation set, and test set with certain allocated number of data points. And then for each realization of these networks, we are going to do validation. And basically, we are going to perform grid search over a pre-chosen hyperparameter space. And we try to look for hyperparameter values that can minimize the root mean square error on the validation set. And then this will give us an optimal network model for predictions. So this is for one realizations. And the idea is that we are going to actually repeat this many times. So we are adopting the approach of ensemble learning, basically. So we are going to do this for many networks. And then we take the final predicted final predictions to be the weighted average values of these predicted values. So the idea is that, again, we do validation in this way, and then we are going to use ensemble learning to get the final predicted prediction results. So this is the picture, basically. So again, we start with a given time series for the slow variable x. And then first step, we are going to extract the fast driving signal from the data for x. And then we are going to split this into training set and validation set. And then there's this model selection procedure here. And then after that, we are going to, so we train basically many independent networks and then get multiple prediction result. And then, so this is the multiple prediction result. And then we are going to take the average, appropriately average path as the final predicted prediction models. So there's a basic idea behind our method to predict right events. So let's go back to the first example that I showed you. So recall that it's basically a bistable system driven by a fast Lorentz tree system. So this is the parameter values that we choose to generate the data for x. And then the data for x looks like this. So so now we work in our assumption. So then it means that we are only given data before the time t equal to 37 here. So in this segment of the data, we the data does not record any occurrence of the transition events. And we want to be able to use this segment of the data to predict this transition using the method that I just told you earlier. So this the results basically. So we compare our result with the baseline. So the baseline here is that we just simply use the data for X, and then we apply. We use the data for X in the eco-state networks without extracting the fast signal. So it's a direct method of simply applying the eco-state network, and the result is, as you can see, is really bad. So there are two scenarios here. So the first scenario is the one with the number of data points in the validation set is 10, and this is another one is 20. So this is just two scenarios, but anyway, in either cases, with the baseline method, the result is really bad, and we are not able to predict the transition. But with our three-step method that I just told you, then as you can see from figure 1A, 1B, we are able to pretty confidently predict the transitions. Moreover, we are able to trace the transition path really confidently. So this here, the light blue shaded region represent the 90% confidence interval, and the red curve is a target path. The blue curve is our predicted path. So as you can see, it works pretty well. So this is for the case when we have 3,700 data points. So it's like t equal to, so data from 0 to t equal to 37. And this is the performance. And let's say that if we reduce the data points, the number of data points to 3690, then it's still pretty good. But if you further reduce it, so after some point, we realize that the result is not so good anymore, in the sense that the predicted path start to deviate from the target transition path. But it's actually not too bad, because if you look at 3B, it still shows us that the predicted path actually, so eventually it goes past 0, x equals 0. So it somehow indicate that the system will transit to another stable state, even not doing so in a confident manner compared to 1A to 2B. And so here are a few discussions. So I would like to emphasize first that this problem of predicting the transitions is actually much more challenging than that of simply predicting the second component of a Lorentz 63 system from the numerical data generated by the system itself. Because why is it so? Because remember that in our method, right, in our three-step method here, so remember that we first need to extract the fast signal from the data for X, and this actually so depending on the quality of the data that you have, then there will be some numerical errors, right, in this step. So basically, we are using sort of like a noise corrupted version of data to predict this second component of the Lorentz system. So that's why it's much more challenging than predicting the Lorentz system from clean data. But in any case, the result is not that bad, as you can see. And in fact, if you look at figure 1A to 2B, the method is actually quite confidently able to predict the right event at least 162 numerical time step in advance. And this is about like 32 autocorrelation time of the fast driving signal. And so what's the lesson here? The lesson here is really that if we compare all these with the baseline methods, which really just fail to predict the transition event, it tells us that it's very important to take into account the multi-scale nature of the system. So that's why in our methods, we have the first step of extracting the fast signal from the data for X. If we don't do that, as in the baseline method, then the result is very bad and we are not able to predict the transition events. So again, the multi-scale nature of the system need to be taken into account when doing all these predictions. So this is the first example, which is pretty simple. We wonder if so what happens if we try this on systems that are more complicated. So let's say we consider the following system. So this basically again is a slow fast system. Now the deterministic force field is actually it's not bistable, but it's a tri-stable system with like triple well basically. So the initial condition is just it's very near the origin. So it's a triple well system with left, center, and right potential well. So for this data, we are going to start the system in the center potential well. And then we want to predict the transitions basically. So it's very important to, because here we start near zero. So after some point, it will either jump to x equal to 2 or x equal to -2, right? So we want to be able to predict the transition and also predict it correctly. So in this case, we want it to we want the method to show us that it is able to predict that the system will jump to x equal to 2 and not x equal to -2. So this is a bit more complicated than the last example. And then we also add a periodic forcing here, the A cosine omega t. And the fast signal here is an Einstein-Uhlenberg type process. So Z here is a like Einstein-Uhlenberg process. And then the Y2 is again the second component of the fast Lorentz 63 system. So this is just to summarize, it's just a higher dimensional version of the system in example 1. And with a more complicated deterministic force field here. So if we apply our methods to this to the data generated from this system, then the following is the result. So again, if we just apply eco-state network directly to the data for X, then we are not able to predict the transitions. And using our 3-step method, we are able to do this. So as you can see from figure 1A to 2B, you can do it pretty confidently. But again, if you reduce the number of data points, then we start to see some deterioration in the performance of the method, in the sense that the predicted path deviate more and more from the target path. So this is, I think, the fundamental issue here is because of the short-term forecasting capability of the eco-state networks, which is true for any machine learning algorithm anyway. So you are not able to predict too far into the future. And then, so this is still pretty good because we are able to predict the transitions pretty well. So now we ask, are there any examples of systems where we are not able to do this? So we are not able to predict these transitions well. So let's look at this system here. This is much more complex than the earlier two examples. So again, this is a tri-stable system subject to a periodic forcing, but with the fast driving signal now comes from, so psi1 is the first component of this multi-scale Lorentz 96 system. So here, this psi is basically a 36-dimensional system. And with these parameter values that lead to chaotic dynamics, as mentioned in the Lorentz original paper on this. So what if the data for X is generated from this system, and then can we, in this case, predict the critical transitions? So this is a sample. This is the data that we have. So again, we want to use a segment of the time series before the transitions to predict these transitions. So now, as you can see, the baseline method is expectedly not going to do any good. And then with our three-step methods, at least in figure 1A, it still do pretty well. But for the first scenario of using validation data with 5 points, but in the second scenario, it's not able to do well. In fact, it failed to predict the transitions. And so this is for the case with this number of data points. And if we just reduce the number of data points by 2, then we are not able to predict the transition events at all for both scenarios. So this just shows how sensitive is this eco-state network in doing all these predictions, especially for these very high dimensional systems here. And not just because of the high dimensional nature of the system, because remember that we are really working with a set of data extracted only from one of the components of the Lorentz 96 system. And more importantly, right, these data are noise corrupted because there's a step that involve extracting the fast signal from the slow variable, from the data for the slow variable. So if we do not extract this signal properly, then there will be a lot of numerical errors. And then if you use this noise corrupted data for predictions, of course, the result will not be good. And in fact, it will be almost nonsense, right? If the noise is too large in the extracted signal, for example. So just to conclude, so here in this talk, we have presented a data-driven machine learning-based method to address the task of predicting noise-induced critical transition events in a wide class of slow-fast dynamical systems. And these slow-fast systems can be related to stochastic dynamical systems by deterministic homogenizations. So basically, we propose a simple three-step procedure that involve extractions of the fast driving signal from the data for the slow variable. So we are basically trying to separate the time scale from the data. And so using this method, we demonstrated our methods on 3 different examples. And as you can see, we saw some successes and also limitations, which is actually a good thing to see here. So what this means is that this actually opens up a wide range of interesting directions for future work. Because in our setting, we made some rather strong assumptions, and there are other more general setups that we haven't considered yet. So for example, what if there are more than 2 time scales present in the generating system? What if the noise is not additive but multiplicative? And what if now the data there are some data missing, or the data is uneven? And also, I think this is pretty important, is that can we come up with a better learning algorithm for doing all this? So maybe rather than using reservoir computing-based approach, can we look into some other learning methods that can do this better than the results that better than we do here. And you can find all the other details and the experimental setouts in this paper that has been just settled in chaos. And I think that's all I want to tell you in this talk. Thank you very much for your attention.
Yeah, thank you very much. Any questions?
Yes, I do have some questions, actually two, to be more precise. The first question is about, I think, your slide 17, where you describe something related to training a deep equal state network. I don't know. And the question is quite simple: is there any intuitive idea or theoretical explanation? Oh no, it's not 17, but okay, anyway, the question is there any theoretical explanation to, if you take several realizations of your network, taking this metric of optimization with respect to the average of this realization of the states, you believe this will convert to the actual behavior of the input data you put? Is there clear my question? Or
yeah, so two questions, right? So the first one is there any theoretical understanding behind this D equal state network? So my answer is that I think there are many ongoing works that try to understand not just the D equal state network, but Shalow equal state network is already there are already many theoretical issues that people try to work on. And yeah, I think there are a bunch of papers by I think Ortega and his collaborators. So they try to work on well, mainly like as a mathematicians, they work on the mathematical aspects of these networks. And I don't think they have looked at I don't think they have studied the version of equal state network yet. But I think, yeah. So I think there are not really a lot of works on like trying to understand theoretically, I mean, this deep version of the equal state network. But intuitively, if you think about it, this is sort of like what happened in deep learning, right? So if you increase the number of layers in the networks, you get better expressiveness, right? In the sense that you know, you are able to better represent the data that you have. So that's why here, yeah, this is sort of like, this is not like a theorem or anything. This is just a intuition here, right? It's a claim that if we increase the depth of the ESM, then we can possibly, right, we can get a better multiple timescale representation of these temporal informations. So the short answer is that no, there are really I think no works that address the theoretical part of this D equal state network. There are a lot of works that try to show experimentally or empirically that D equal state network can work well, can work better, in fact, than the Shalow version in many parts. So yeah, this is a short answer that I can give you for now. As for the second questions,
which is taking the average over the all realizations of the network, and then you optimize the linear regression problem with respect to taking several realizations. So why this? Do you believe this is a good metric to approximate the input data you are trying to solve?
Like according to my understanding, so this is, I mean, what people call ensemble learning. So in the sense that, sure, you can produce the predicted model by just running, I mean, one realization of the network, sure. you can do this. In fact, this is basically what people have been doing all the time in deep learning. Like, let's say that they have LSTM or GRU, and then they just try to do this and then get the result. And the point is that in their case, they don't do this ensemble learning because it's very expensive to run even the one network, right? Because there are many parameters to be trained. And so in the deep learning case, they don't do this. In our case, we do this ensemble learning because the reservoir computing frameworks allow us to do this in a very short amount of time, and it's very computationally inexpensive. So that's why we can leverage the power of ensemble learning in our case to perform the predictions. And the point of doing this ensemble learning is that it reduces the variance of the predictions model, basically. Because if you see, so this is basically randomized networks, right? So depending on, the realization of this network, you get different prediction result, right? Every time you train it. So to be able to capture the uncertainty in the prediction result, right? It's a good idea to perform this multiple times for independently trained networks. So then we are able to assess, right, the uncertainty of the result produced by these eco-state networks. So that I think the main motivation behind using this ensemble-based learning is to reduce the variance in the prediction result and to quantify the uncertainty, right, in the predicted results. And yeah, does it make sense?
No, yeah. Okay, I would think about it and search for ensemble learning. And the last question, I lied. I had a third question, which is with respect to this highlight dependence to the how many data points you use to estimate. So my intuitive idea was there's a step of restricting the f of t that
Yes.
you even mentioned maybe is not quite good because you may do some wrong, then you corrupt by noise intrinsically trying to estimate this. So the question is, there's any way to extract the time scale of this model you're using, underlying model that you're using to simulate X? So is it possible to extract this epsilon and sigma scale from in the step 10? And this gives you some answer about how many data points you will need for sure to guarantee the reconstruction. Because in this last example, you miss only 2 points. Another one is 30 points, and then you messed up completely. So is it any possibility to estimate the scale of the underlying dynamics, the fast one and the slow one, from this step 10? So that's the last question. Thank you so much.
Yeah, thank you for your questions. Yeah, I see your point. So the thing is that, like, because of the assumptions that we have here, right? So we only assume that we have data for X, and we know nothing about the fast driving signal at all. So we know nothing about the sigma, the noise amplitude in the system. We know nothing about the epsilon. We only have data for X. So if you look at the data for X, yeah, for example, in this case, I would say like it's pretty difficult to extract the time scale of the fast driving signal, although I haven't tried it yet. So so that might be a good idea to look into, right? Can we extract the time scales from here and then use this time scale to do something?
Yeah, just to make sure to match. You take the toy example, this first one, and see if they match with the natural timescale you had from the underlying dynamics, and then you apply to this difficult one. And then you will say, oh, if I miss 2 points, it's quite important for me, so I can't. Then you gave some natural, self-consistent approach in this. I mean, that was my idea. When you just miss 2 points, oh, everything blows up, then try to extract this natural timescale of this low dynamics that you mentioned.
I see.
Oh, and the fast dynamics, sorry, and the
Yeah.
fast dynamics.
Yeah, that's something that we can look into. Yeah. Thanks for.
Okay, thank you so much. Congratulations. Thank you so much.
Thank you.
Any other questions?
Yeah, actually, sorry if I can.
Yes. Yeah, go ahead.
Ask one short question as a guest.
Sure.
So yeah, thanks a lot. This was a very, very clear and fascinating talk. I've actually worked a little bit on related things from the theoretical side on homogenization problems, and we worked out something in a mild way where the fast process is also allowed, or the fast system is also allowed to be coupled to the slow system itself. So in your case, you have this kind of skew product structure where the fast system is not really depending on the slow one, right?
Yes.
But exactly. But here in your case, the psi might also, the h might also be a function of x and not only of psi. So I was wondering, have you thought about trying some examples also for this case? And because I would assume that your methods, your machine learning methods using this echo state network, they should be quite stable with respect to that. I mean, analytically, it's very, very hard to make extensions here when psi depends on x, but I would assume that your computational methods could achieve quite a lot there. What do you think?
You mean when like in the capital H, there's dependent on x?
Yes, exactly. If it's not only this kind of external signal, but if there's really, I mean, there might be many examples where you have a full coupling, right? Where this is not only easily separable into these two scales that way, where the psi is completely external, but the psi might also be in a coupled or some sort of weak coupled correspondence with x.
Like the first thing that comes to my mind is that this method will not work if the data comes from that system. Just because like there's I think it will not work, but I could not say this with certainty because I haven't tried it yet, but I think it will not work as well as the one that I show you here.
Okay. But as such, I mean, you could make, I mean, you were always collecting the data concerning the external signal, and if now this would, if the signal would always also depend in a certain way on x, so maybe I mean, I'm not deeply into your into your algorithm. I just it seemed to me that this was not such a big obstacle. But why would you say that this will not work? Why do you think?
Because the assumption is that so the fast driving signal comes from a completely different dynamical system. So it's not coupled to x at all. But if it's coupled to x, so then basically well, I mean, then it's a bit, because we are trying to separate the fast process from the slow one. So the slow one here is x and the fast one is psi.
Sure, yeah.
So with this separation, so actually this, the fact that we're able to do this, like separate the time scale, so from x from psi, is a crucial factor that enable this method to work well. But
no, that is clear, of course, that you have a separation of timescales, but that does not exclude that there's a coupled dependence. I mean, the fast timescale can also depend on the slow one.
Yeah, I see. I see a point, but I don't know. I need to try and see what happens.
No worries. I was just curious. But of course, it would make it, I guess, in certain ways harder. But I had the hope that maybe, especially with your form of approach, it might even be easier than doing some things analytically. But yeah, anyway, yeah, thanks.
I see a point. Yeah. Thank you for the suggestions.
Hello.
Questions?
Yeah, hello.
Hi.
Maybe I can ask. Thanks for the nice talk. I'm Kalle Temperi from Imperial. And so, so I was wondering about this, the first and second example that you showed there at the end, and in those cases where it seemed to work, the method, but it looked like it was in the second example, for example, the maximum likelihood level was somewhere between the 0 and the 2. And I was kind of surprised because it seems like it's like at the unstable regime between the two wells. And is this because of the kind of short-sightedness of this network that you said that it can't predict over long time scales, or or why is it that, why is it like that? For example, here in this 1A and 3A, the blue is like between, blue is sitting at 1, right? But whereas in 2B, it goes very close to 2, and in 1B as well.
I think like in 1A is close to 1.5.
Mm-hmm.
So it's actually still pretty good, even though it's not perfect. Yeah. Yeah.
I'm wondering why does it stabilize there, and why does it stabilize in 3A? It stabilizes at 1, right?
Yeah. Yeah, I think it has to do with this short-term forecasting capability of the ecostate network that I mentioned. In the sense that if you go further into the future, the quality of the prediction is going to get worse.
Okay.
This is actually, yeah, it's a common issue in all time series prediction methods based on machine learning. So
right.
we are able to capture
one should think here that there's some kind of a reliability measure to this, which is going like lower and lower and lower when you move right towards the right in these figures somehow because of that network property. Is it so?
Like I don't quite understand your question. So
sorry, no, I was just asking how to kind of how to see that in these pictures, like exactly, you know, this property that the long-term estimation becomes more unreliable.
Yeah, like this is sort of like the intuitions. Yeah, okay. Yeah, I think also it has to do with how we train the model. But yeah, okay, I see your point. I see your point here now. Yeah, like if you compare 1A to 2B, right, for example.
Yeah, exactly. Yeah, I was wondering like if you have like an easy answer to like why they are different, or maybe there's something interesting there actually. I don't know.
Yeah, I have no answer to this. Yeah, like I see, but I see your point. Yeah. But yeah, I have no answer to this. Yeah, but the point is that yeah, the point is that it's sort of like it's able to indicate that a transition will happen pretty confidently, even though it's not like tracing the target path.
Of course, yeah,
perfectly,
yeah,
but but I see your point. That is more for the machine learning, from the machine learning point of view, right? Why 1A and 2B has this different behavior.
Yeah. Of course, if these graphs already indicate that there will be a transition with a high probability, and that's all that you're interested in, then it doesn't really matter, right?
Yeah.
That's where it is. But it would still maybe be good to understand why that is. Yeah, I don't know.
Yeah. Because I think there might be many factors at play here, because the way we train this model using this the model selection procedure that I mentioned briefly. So there might be something hidden there in the model selection procedure, like how we select the model and then how we do the average. And how do we average the predicted values. So yeah, there might be something there that we can look into. But other than that, yeah, I think really the answer is in the model selection procedure. Yeah.
Okay. Yeah. Thanks.
All right, thank you. Any other questions? Actually, I had like a small question. I mean, since you are using an echo-state network, it's or I mean, in general, when you are using this deep neural networks or this kind of thing, I mean, you have like an expression of the solution in some sense that you are using. Like what you mentioned in I think slide 17 or one of the slides, you already have can express. Yeah, exactly. So, for example, you have the output as a function of the input, and I was wondering if you played with like you plug in these expressions in some toy model and see what happens. I mean, if you are able to get sort of theoretical results, but just plugging directly, right? I mean, just very simple thing. We have to plug in 16 in the equation in the SDEs themselves and see what happens if you can get some analytic results for simple toy models and then sort of universal approximation or these kind of things. I mean, did you try this or?
No, not yet. But yeah, I think that's a good idea. Yeah.
Yeah, just to get a sense of what's really going on. I mean, with the choice of activation function, parameters of the network, and these kind of things. So maybe
that's a good idea.
Yeah.
Yeah, but yeah, we haven't really talked about that yet. Yeah, we just want to apply this and to this problem. Yeah. Thank you. Yeah, for this good idea.
Yeah. Anyway, so if there are no other questions, then thank the speaker and thank you very much. Thank you.
Thank you.
Yeah. Thanks. Okay. Thanks a lot. Take care. Yeah. Thanks. Bye-bye. Bye.
Thanks.